All right, we'll go from this current slide. Now this is example 2, which is way, 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 way back in the text. Okay, here's Jesus coming in. So let me get Jesus here. Got Jesus here. By the way, the bottom part of the alphabet is coming in very strongly. The top half's not too bad, but the bottom half's got a big block of people there. A good way to go. Okay. This is example 2. We've moved way beyond that. And let's just see what the next slide will be. Nope. Nowhere close yet. Okay. So let's go back. Okay. We'll go right there. All right, where we are is example 5 on page 448. Oh, by the way, time out before we get started. We're the test that's out there, I hope all of you were able to get. Were any of you able to open the Word document? Did it open okay? I know some of you it would not open. I believe it was Alea or somebody sent me a copy of what came out, and it was terrible. Were any of you able to open the Word document, or are all of you using the PDF? Anybody? Has anyone opened? Yes. Okay, and it had the integrals and everything in it? Okay, yeah, I think what it is, it must be the version of, whoops, here's Anita coming in. So let me get Anita here, and we will go from there. All right, that beginning to block off the top half of the alphabet fairly strongly. Middle part still has some gaps in it, but it's coming across as a good class today. Okay, I'm glad that it worked at least for somebody, because it looked perfectly good to me, but I know some of you it did not, so good to hear. All right. So let's do, like I was saying, we're in Chapter 7, Applications of Integration, Section 7.1, getting near finishing that, area of a region between two curves, and then, because in the last chapter we did, Chapter 5, we did area under a curve. Now we're doing area between two curves, and example 5, top of page 448, is find the area of a region bounded by the graphs, and it gives the two graphs here. Now we haven't done this one, right? Now I'm going to see if maybe oh, look at that. It looks like maybe. Okay. Let's see if, hey, looks like maybe I can write on this. Now my ink color right now is red, it appears. I just as soon have black, but I'm sort of new at this. So let's see if I can get control. I don't know what that means. Windows key. That's probably not it. Okay, I was better off where I was. So let's go back here. All right, let me see. Well, now I can move there we go. All right, let's see if this works. Okay. All right. I'm going to see if I can get the pen to come down where I want it to be. And, well, it's not drawing a line. Oh, there we go. Now, she has it set very fine. I've got to figure out a way to go back and set that, but I'm not going to waste time today. So here's what we've got. Find the area of a region bound by these graphs. Okay. X. Well, that's not working well. So I think maybe what I'll do is get out of this and go to the whiteboard. And let's see if it'll work better there. Okay, now I've got some fiddling around to do with the whiteboard. Y'all are my guinea pigs today. This is the very first time I've used this Wacom. Now, I've used Wacom products before. In fact, the old Fujitsu computer I had was Wacom equipped, but this is the first time I've used a box like this. Okay, so there's my pen, and let's see if I can I think I'm going to have to fiddle with this. I think I want to get to draw mode. Okay, that's ugly. I may quit this if it's too bad. Find the area of the region bounded by the graphs of x, whoa, this is bad, is equal to 3 minus y squared Now, can y'all hear me fine? Because I'm over to the side here so I can write on the Wacom, but I've got my headset on, so are you able to hear okay? Okay, I assume that means yes. Maybe you can't. And the other function is x equal y plus 1. Okay, now find the area of the region bounded by those two graphs. The fact that they give us the graphs as functions of y, x is a function of y, that will indicate we probably need to do our dy's here, delta y's, not delta x's. So we need to see the points of intersection, and you remember how we got those? Anybody? Okay. I'm going to do the second one first. Y plus 1 is equal to 3 minus x squared. 3 minus y squared. I'm so used to doing it. Okay. I'm doing it again. Y squared. That's a y. Okay. I'm just as bad writing with my left hand as I was with my right, am I not? Okay. That's a y there. Y squared. Okay. Now, what we need to do is move everything to the left. So that would be y squared, when they add y squared to both sides, plus y, and then subtract 3 from both sides, that would be a minus 2, is equal to 0. Okay, I can slash my zeros again. I feel so good. All right, what would you do at this point? Please someone say something. What's the F word? Uh-oh, have I told y'all that yet? When I say what's the F word, that means factor. Excellent. Okay, some of you have been in my class before. Okay, I may have said it in here before too. Can we factor this? What's the only possible factorization for y squared? Y. Got it. Y times y. Okay, where we look next is the sign of the last term, a minus sign. What does that tell you about these two signs? Okay, one's a minus and one's a plus. They've got to be different. I'm still not writing too well with this. Okay, now we have to deal with the numbers. We need two numbers that multiply to be 2, but because they're different signs, their difference is 1, plus 1. What do you reckon those two numbers would have to be? 2 on the plus side and 1 on the minus side. Why? Because the plus wins here, so it needs a bigger number. 2 times negative 1 is negative 2, and when you FOIL this, you get y squared plus 2y minus y, that's plus y minus y squared. Yeah, that factors. So what are our 2 points of intersection? If I can get the pen to come on down. Okay, every time I touch the screen with my hand, it screws it up. And I'm left-handed, so I always am touching. Okay, so this is going to be a y equal what from the first term? When you set each of those equal to 0, do I need to do that? I'll be glad to if you'd rather see it. Come on, someone answer me something. You need to see me work it out, or? Okay, all right. So let me go back and get my eraser, and I hope the eraser will work now. Well, where did you go, Joe DiMaggio? Okay, there we go. Okay, nope. Close, but no cigars. Let me see if putting this on the computer keyboard might work. I'm going to move things around this. Like I said, y'all are guinea pigs today, so I'm trying different configurations to see what might work best. Sorry about this. Okay, let's try this. See if this works any better. Okay. It gets so close. Okay, now we got the eraser, I think. Okay, and go back to the draw mechanism. Well, while I've got the eraser here, let me erase that and get draw back again. Okay, so what we do here, we've got two entities that multiply to be 0. What does that tell you? Two entities here, y minus 1 and y plus 2, they multiply to be 0. What does it tell you about those two entities? At least one of them, it's got to be 0. So that's what we're doing here. We say either y minus 1 is equal to 0, or y plus 2 is equal to 0. Okay, one of those two. I'm not going to slash 0, it's too hard. Okay, this first one, what does it tell you? What would you do to solve that equation? Okay, no, let's not go backwards with it. You add 1 to both sides, right? You're trying to solve for y. Add 1 on this side, add 1 on this side, and now these two add, if I could get the pen to write, to be 0, and that gives you y is equal to what? 1. 0 plus 1 is 1. Over here, what do we do? This is pretty elementary math, right? Subtract 2 from both sides. And that gives us, here the 2's go to 0, plus 2 minus 2 is 0, y is equal to 2. Negative 2, okay, sorry. Subtract 2 from both sides. All right, so here are the two places where these functions intersect. Now, good idea what you were saying earlier. I didn't catch who that was saying it. If you plug these values back in your original functions, and here's the easy one, that's the one to do. When y is equal to 0, y is equal to 1, x is equal to 2. So if I can get the pen to come down here, x equal 2, so that's at point 2, 1, and when you plug in a y is equal to, come on, you can do it, get on up there. Okay, plug in a negative 2 here, x is equal to negative 1. Okay. I've got to find a better way to get this to right. Okay. So let's just try the other side and see if that works too. when you put a y equal 1 here, 1 squared is 1, 3 minus 1 is 2. Yep, that works there too. And when you put a negative 2 in here, here, 3 minus a 4, negative 2 squared is 4, 3 minus 4 is negative 1. So x equal negative 1 there. So those are your x, y pairs. Okay? Now in both cases, this one is to the left, that one's to the right. This one's on the downside, this one's on the upside, depending on whether you're looking at x's and y. But since we're doing delta y's, that's what we want to do. Now, you need to figure out which of these two functions is, and since we're doing horizontal line bars, rectangles here with delta y's, okay, what we need to do is find out who's on top here, okay? And let's see, let's plug a number in between y equal 1 and negative 2. Can someone think of a good number between negative 2 and 1? Make it an easy number. Between negative 2 and 1. Anybody? 0, are one of my favorites, okay? When you plug a 0 in for y here, x is 1. When you plug a 0 in for y here, x is equal to 3. Okay, so it sure looks like the quadratic is on top. Okay, I mean, actually to the right. Okay, the linear is to the left. Now, if you look at the picture in the book, you'll see that's indeed true. Okay, so therefore we do right minus left. Just like before we did up minus down, right minus left. Well, the right is the quadratic, so the function we're going to be integrating here, if I can get the pen to do it, is the integral. Now we're doing dy's, so y is going from negative 2, that's the lower value, up to 1, that's the upper value, and then we do the quadratic first, 3 minus y squared minus, this is the length of the rectangles now that we're doing here. The right hand end is the quadratic, the left hand end is a linear, and that's minus y minus 1. Is it alright for me to do that rather than having to write 2 steps there? Minus y minus 1. It was minus a y plus 1 in parentheses. I just did that. And then we have dy's. That's the length of our rectangles, that difference there. Okay, come on up here. Okay, there we go. Okay, and then we'll have a dy here. Okay, it seems to be doing a little bit better. Okay, so let's redo this integral. The integral from negative 2, y going from negative 2 to 1. Does everybody see what we're doing now? Okay, I'm going to combine the like terms here. Okay, 3 minus 1 is 2, minus y squared minus y. And that's what we're integrating dy. Still can't draw these very well, can I? Okay. Now, what's the antiderivative? This is where the calculus comes into play. That's all been algebra so far. What's the antiderivative of 2? You're integrating with respect to y. Anybody? Antiderivative of 2? No, 2y. You got to have your variable in there. Okay? Do you see that? Okay. The exponent for the y here, you don't even see a y, do you? That means it's y to the 0th power. Increase that exponent by 1, that makes it to the first power, and divide by the 1. Well, you don't need the first power and you don't need to divide by 1. So that's just 2y. Okay, what is the antiderivative of y squared? I'll give you a hint, there's a y in it. I can't get the writer. Y what? Not fourth. not fourth. Increase by 1. Increase the exponent by 1. 2 plus 1 is 3, right? So it's y cubed over 3. Okay, how about the next term? What's the antiderivative of minus y? Hint, it's got a y in it. This is the one you wanted to do before. Y squared over 2. Excellent. Okay, now we're going to evaluate these between -2 and 1. Okay, now let's do the 1 first. 2 times 1 is 2, minus 1 cubed is 1, so that'd be 1/3. Everybody see what I'm doing? Minus, okay, 1 squared is 1, so that would be 1/2. Okay, now we're going minus, okay? So I'm going to put down the minus, understanding it's going to change signs like crazy. The minus there is because we're using the lower limit here from the fundamental theorem of calculus, okay? So when I plug in a -2 for y, 2 times a -2 is -4. But you already got a minus sign in front, so that becomes a +4. Does everybody see that? Okay. Now, plug in a -2. Okay, remember, we're still minusing because we're using the lower limit. Plug in a -2 for y. Cube it, that would be a -8, okay, but you got another negative sign here, so you have a minus, that would be a plus, and then another minus that goes back to being minus 8/3. Now these minus signs are there to trip you up. That's their only purpose in life, is to trip people up, and I think they do a really good job of it. Okay, now we do a minus again. Okay, but this time this minus is going to change that to a plus, and when you plug in the -2 for y, -2 squared is +4 divided by 2 is 2. Okay, does everybody see those plugs? Okay, you have a heard something going on, but I can't tell what it is. I thought my phone was buzzing at me, but it doesn't seem to be. All right, let's see what we can do, combine like terms. Okay, come on down here, pen. Okay, here we have a 2 plus a 2 plus a 4. That would be 8, right? And then we have a bunch of fractional minus signs. Well, first, -1/3 and -8/3, that would be -9/3, which is -3. So I'm going to put that -3 down here. And then we got a -1/2 we haven't accounted for, so we're just going to do a -1/2. Okay. This isn't as easy to write on as I was told it would be. I can't get it to come down here. Okay, there we go. All right. 8 minus 3 is 5, minus a half would be 4.5. Okay, that's the easy way in my mind to do it, but I bet you they give the answer in, what do they call it, improper fraction, which would be 4 times 2 is 8 plus 1 is 9/2. That's my guess of what the answer is. Let's see what they got. Oh my goodness, look at that. That's what they got as well. Okay. Now, any questions on this before we go back to the PowerPoint? Well, we can't go back to the PowerPoint. They don't show it on the PowerPoint. Sorry about that. Now, time to do this again. I didn't want to draw the graphs, so I'm going to show you the graphs. Okay, if I can get it up here. Okay, there are the graphs. We did the dy's like this. See, there's a quadratic, which is a parabola lying on its side because it's y is a function of, x is a function of y, and then there's the straight line, That was the left hand side. And we did our rectangles by the quadratic minus the linear. That's why we did the integral the way we did. Now, we could have done dx's, but see what a mess you would have then. For the side over here, I don't know if I can get my finger in there, the side over here, it would be the linear part on top minus the quadratic on the bottom up until the point 2, 1. Okay, I couldn't read it on the book, reading it backwards here. And then from there on, you're doing the upper part of the parabola minus the lower part of the parabola. And that's a real pain in the neck to do that integration. So who would want to do that one when these are, that one is straightforward. Now some texts call these type of integrals here, I can't think exactly how they phrase it, integrably simple. Okay, it's integrably simple to do the y's, delta y's, because there you're going from one graph to the other graph. I mean all along. Okay, it's not linearly integrably simple to do from the top of one graph to the bottom of one graph. That's a pain in the neck. So if you can, always go with the simplest. That's always my doctrine here. The bottom part of the page, if you have the book, it shows that using the dx's, and it's really a pain in the neck. And anyway, that's there. All right, any questions on that? Now, there were, I think I got at least one question over the weekend about question 2 on the test. It just did dawn on me that I got that. I answered that one. I think I'm not sure if it was, which one of you it was. It seems like it was one of the guys that asked a question about that. Did my answer, was that satisfactory? You may not be here today, whoever the guy was that asked. Was that satisfactory, or did you need more explanation on question 2? Oh, that's right. It was you. Okay, and that was okay? Okay, because I didn't know for sure if you had a book or not, because I told you at the beginning of the term, the whole class, if you want to hang on to your calculus book you came from your parent school, then by all means do that. And I was just guessing that might be the case, that you didn't have that, but that's why I gave you the references on the websites. Okay, great. Glad that happened. I forgot about it till now. Okay, let's go back to the PowerPoint then. Well, I was rubbing on the Wacom, not on my mouse. Okay, so let's go back to the share. Okay, you tell me, did you like the Wacom and my writing with the stylus better or worse than my writing with my finger? You tell me. Anybody? I thought so too. Thank you. I didn't want to go back to writing with my right index finger. Okay. All right, let's go back to here. So we've already finished long since past. Here's where we are on the top of page, and we've lost our slide. So let's go from current slide, and we'll have to go here. We'll get there in a minute. My goodness, that was the same answer we just had, and that was a different problem. Okay, integration as an accumulation process. Okay, this is on page 449 and following here. Okay, the integration formula. Oops, is someone coming in, or is that just popped up there? I guess it just popped up. We should have 13 people here, do we? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, must have somebody come in I didn't catch. Let's see who it is. Okay. Oh, no, somebody left. That's what it was, because I have more people here. Okay, forget that. Okay, someone must have gotten booted out. I think they're probably going to, if there's not rainstorms in the area, it looks like they're going to be. I was out a little bit at lunch, and it is hot and humid, so it's perfect for a thunderstorm to pop up. Okay, and that may have knocked somebody out. The integration formula for the area between two curves was developed using a rectangle as a representative element, either dx or dy, remember? And then you had a rectangle so high or so long. Okay. For each new application of integration in the remaining sections of this chapter, an appropriate representative element will be constructed using pre-calculus formulas you already know. Okay. Each integration formula will then be obtained by summing or accumulating those representative elements. Okay, so this is a little bizarre. So what we're going to do is known pre-calculus formula and identify a representative element and lead to a new integration formula. I don't know this. We'll see how it goes. To me, this is almost make-up work because what we're just doing works perfectly fine. For example, the area formula in this section was developed as following. Area is height times width. Okay, so your delta area would be the difference in the height. Now this is if you got a dx here. The difference in height, that's f of x minus g of x, if f is on top, okay, and your width was your dx. Okay, then the area, when you integrate this side and sum all the delta a's together, and you integrate this side, and it's just the integral of f of x minus g of x. That's exactly what we did in the last problem, except it was f of y, g of y, and dy. Okay, and our limits then were not x equal a to x equal b, but y is equal to, what was it, minus 1 to b is equal, no, minus 2 to positive 1. Okay, same type deal. Now here's example 6. Find the area of the region bounded by the graph of y is equal to 4 minus x squared and the x-axis. Okay, it says describe the integration as an accumulation process. And frankly, for me, I don't even know why they bother with this. It's basically the same thing we were doing before, but let's see. Okay, find the area bounded by the region of the graph of y minus 4x squared and the x-axis. Well, what we need to know first is what are the limits of this. So let's see if I can get this to do. For some reason it writes red here. Okay, so let's let, when x is equal, when you're on the x-axis, what's your y value? Anyone tell me? If you're on the x-axis, what's your y value? Anybody? 0, of course. Okay, so we're doing, our height is y minus 0. So that's just integrating the integral. And see, this is the real thin line. I don't know why. Oh, wait. Scratch that. Now let's see, how can I erase? I don't remember how to erase yet. Okay, I can't get it to erase. Sorry, it's getting worse. Okay, I'm just going to scrub out until I know how to do that. So what we're doing is y minus 4 equals 0. 4 minus x squared is equal to 0. Okay, well, I'm going to turn that around and make it x squared minus 4 is equal to 0. Basically, why that's legal is I just added x squared to both sides, subtracted 4 from both sides, and wound up with that. Okay, now what are the values of your limits here? Again, factor that. Anyone know what that factorization is? Whoa, this is ugly. I didn't do that, folks. I don't know why it did that. Okay, this is really being difficult to manage here. Okay, it's x minus 2 times x plus 2. That's how you factor the difference of two perfect squares. Okay, and that's equal to 0. What will this give you when you set that equal to 0? Anybody? And the other? Okay, so those are our limits. We're going from -2 to 2. Okay, so find the area. The area would be, where's my pen here? The integral, this is what I started right before, from -2 to 2 of 4 minus x squared. Now we'll go back to writing it the way they said to write it. And then our dx. Okay? And what's the antiderivative of 4? Hint, it's got an x in it. No, not squared. Increase the exponent by 1. The exponent, this x you don't see, it's x to the 0th power. Raise the 0 to 1, and you got x to the first power. So it's just 4x. Think of this. Differentiate this back again. If you take a derivative of this, you get 4, right? So antiderivative would be 4x. If it had a 4x squared there, the derivative of that would be 8x. That's not an 8x, that's a 4. Okay, so it's got to give you what you do if you go back and do it backwards. Okay, now we've got a minus here, and what will be your antiderivative of x squared? Hint, it's got an x in it. X cubed over 3. We're going to evaluate. Why it does that, I have no idea. Okay, maybe it's because my hand's resting on this, I don't know. You're going from -2 to 2. Now, I really wanted to, and I probably should have. If we think back, let's see if I can scroll back real quickly here to something we hit before, but it was a bit in the background. Let me see if I can find it. I bet you it was in the last chapter, wasn't it? Yeah, it probably was. Yeah, it was in the last chapter. Sorry about that. I was going to save us a little effort here, but I'll go on and do it anyway. Okay. All right. Now, remember, what can you tell me about this function right here? Think, what are your superscripts? What are your exponents here? This is an even function. Now picture that in your brain, okay? In your brain, this is a parabola, right? And the vertex of that parabola, the highest point on the parabola, is when x is equal to 0. And it falls off on both sides. So guess what? We don't need to do -2 to 2. We can do 0 to 2, and I can't remember how to erase it. I'm going to have to find that out later. So this is going to be 0 to 2, and we're going to double it. Okay, now that was a trick from before. I can't find it. It was in the last chapter. Okay, so we're just going to do that from there. Forget about the 2 for now. We're going to leave the 2 on the outside, and then let's do the integration here. When you plug in +2 for 4, 2 times 4 is 8, minus, plug in a 2 for the x, and you get 2 cubed is 8, so it's -8/3. And then, this is the beauty of doing a 0 rather than a -2. When you plug in 0, it's 0. That's why I went on and, okay, got to get down here where I am. Okay, so what do we have here? 8 minus 8/3. Well, let's see, how many thirds is 8? Can anyone tell me? How many thirds is 8? Isn't that 24 thirds? Isn't that 8? Minus 8/3? I do math sort of strangely. I do it the least possible work. Okay. Well, 24 thirds minus 8 thirds, believe is 16 thirds. Double that, and you got 32 thirds. Okay. I don't know why. I don't know what this is doing. Goodness gracious. Let's go back here and back up again. Whoa. It it erased everything I had just done. But my answer to that was 32 thirds, if you remember. It was there for a flash and then disappeared. Okay? Now if you go back and watch it on YouTube video, you'll see it. Okay? So 32 thirds is what I got as the answer. Now, here's what they're suggesting you do. And why, I don't know. That was so easy to do that way, or at least I found it easy. Here's what they're suggesting. The area under the curve is certainly that. That's exactly what we did. Okay? And it said you can think of that integration as the accumulation of the areas of the rectangles formed as the representative rectangle slides from -2 to 2, as shown in this figure. Okay? It's exactly what we were doing. Okay? Now, why would you do this? They would say, let it slide from, sorry, I was using my Wacom as if it was my keypad here. Okay, they say, do first the integral from -2 to 1, and you do that. Why? It's so much easier just to do twice from 0 to 2, and then you have to do it from -2 to 0. Well, that's fine too. Okay, at this point right here, when I did -2 to 0, I wouldn't have ever done this one. Do -2 to 0, stop right there and double it. 32 thirds is what you get. But what they're saying is you let that rectangle keep sliding on over here, and then they stop and do another calculation here. Why? It's so much more work, I'm not sure. And then you finally do the last one, and that's what we did in the first place. So yes, that is what's happening here. You're accumulating the area as you go up the curve and then come down the curve, and accumulating all that area till you get to the end. Well, why in the world think of it this way? Well, no, -2 to 0, double it. Okay, that right there would do your problem right there. Now I did 0 to 2, just this half, and then doubled it. You got the same answer, 32 thirds. Now, sure, that's happening, but it's so much more work to do it that way. So why would you want to? I don't know. But anyway, let's go on. That's the end of the slideshow. That's the end of the section. Homework exercises here in 7.1, beginning on page 450 and continuing to 453. Do any of the odds 5 through 9, they're all at Calc Chat. Okay, 7's at Calc View. Do either 11 or 13, they're both at Calc Chat. 11's at Calc View. Do any of the odds 15 to 27, they're all at Calc Chat. 17's at Calc View. Do 29, it's both at Calc Chat and at Calc View. Try to do 31 to 35, they're all at Calc Chat. Okay, now the indicator here says you might need to use a graphing utility. I think you can probably do it without that, but that'll be up to you. You try. Then do any of the odds 37 to 41, they're all at Calc Chat. 37's at Calc View. 43 or 45, they're both at Calc Chat, and again they suggest you might need a graphing utility. If you do and got one, use it, otherwise don't sweat it too much. 47 or 49, both at Calc Chat. And again, they say you might need a graphing utility. Then 51 at Calc Chat. Either 53 or 55, both at Calc Chat. 53's at Calc View. either 57 or 59, they're both at CalcChat. 61 or 63, they're both at CalcChat. And you can explore doing 65 or 67 if you'd like. Okay, it's exploring a concept. You can do it if you'd like. That's up to you. They should both be at CalcChat. Excuse me. Then you could do 69. It's at CalcChat. 71's at CalcChat. 73's at CalcChat. 75's at CalcChat. And then they have in 77 a Lorentz curve. Now that has a indicator that you might need a graphing calculator, but even if you don't do the problem, who in the world was Lorentz? That could be a potential paper topic. And by the way, I did receive at least one paper in today, I believe. Maybe more, but I wasn't able to finish checking emails this morning because the dean came up with huge projects for us to do, and I'm also trying to get my faculty evaluations done. So the morning was shot. I got a few things printed, but nothing graded. But if you haven't picked a paper topic, who was Lorentz? How did he develop this curve? Who uses it? Well, the problem says economists use it. So if any of you are going into, say, industrial management or anything such as that, you may wind up using a Lorentz curve. So if you want to, follow up on that one. Okay, 79 should be at CalcChat. That's a building design problem. 81 should be at CalcChat. 83 and 85 are both true false. They should be at CalcChat. 87 is the Putnam Challenge. I'll let you decide whether you're going to do that or not. You don't have to by any means. All right, now where we're going now, we're finished at 7.1. Any questions on 7.1? Yay or nay? Okay, I don't hear any, so I'm going on to 7.2. Okay, hold on just a minute. I'll get the screen sharing back. There's 7.2. All right. All right. Do y'all see my PowerPoint again? I know it flashed off, but then came back on. Okay, good. Okay. I'm going to try to get the slideshow to come up from current slide, and we'll go. Let me also try to move this thing out of the way. Okay. Now, Chapter 7 is applications of integration. 7.1 was basically area between two curves. Okay. 7.2 will not advance until I hit the screen. There we go. 7.2 is going to have you not do areas, but do volumes. Okay. And this will be the first of two methods to do volumes. The first is called the disk method, and you'll see why just momentarily. Here are the objectives. Find the volume of a solid of revolution. Now, what do we mean by that? You have a curve, some sort of curve. Y is equal f of x equal y of x, something like that. X equal f of y or g of y or something like that. You have a curve. You take that curve and revolve it around the axis that is your independent variable. It could be revolved this way if it's y, this way if it's x. Okay, so that's what they mean by solid of revolution. Taking a curve, whatever the curve is, revolving it around the axis or some axis. It doesn't have to be the x or the y axis. It could be the line x equal 3, or anything like that. We'll find the volume of a solid of revolution using what they call the washer method. Okay, now the difference between a disk and a disk is a solid circular shape. A washer has a little hole in the middle. Okay, and that's when you have two curves, and it's a solid of revolution around two curves. Okay, and then we'll find the volume of a solid with known cross sections. Okay, that will come up, I think, pretty easily in the washer once we've done the other two. All right, so let's first look at the disk method. Now here's where they're going to begin, and it seems a little strange at first, but hang with it. When a region in a plane is revolved about a line, the resulting solid is called the solid of revolution, and the line is called the axis of revolution. So here is a region, okay? It's a little region of width W, isn't that creative, the name of width W, height capital R. Now there will be a reason for that to be capital R. It has nothing to do with rectangle, okay? And what we're going to do with this little rectangle you have here, we're going to revolve it around this axis of revolution. That could be the x-axis, it could be the line y is equal to 17, or negative pi thirds, or anything like that. It's some axis of revolution. We're going to revolve this around the axis. And when you do, that little rectangle goes all the way around and shapes out a disk. The thickness of the disk is that same W we had. And now you see why we called that capital R, because that's the radius of that disk. The capital R is the radius of that disk that you went around like this. The simplest such solid is a right circular cylinder or a disk, okay, which is formed by revolving a rectangle about an axis adjacent to one of the sides of the rectangle. We chose the bottom side here, okay? You could have chosen the top side, you could have chosen the left side or the right side. We chose the simplest, the bottom side. Revolve it around, you wind up with a disk, okay? Now, let's think about the volume of that. Oh, they already thought about it. The volume of that disk, and this is the volume of a right circular cylinder, is the area of that disk, which is pi times capital R squared. That's the area of the disk times the thickness of the disk, W. That is the volume of any right circular cylinder. Usually we think of them sitting down on the base here, and that would be your base, and then however tall it is, multiply the base times the height, and you get the volume, okay? The base of a right circular cylinder, though, is a circle. That's why they call it right circular cylinder, okay? So we find the area of the base and multiply it by its width or height, okay? So the volume of such a disk, the volume is the area of the disk, what I just said, pi r squared. Capital R is the radius, which is the, in a sense, sort of like the y value we'll be doing a lot, but it doesn't have to be y value. It's the difference from the top of the thing to the axis, okay? Okay, area of the disk, that's pi r squared times the width of the disk, and that's your W, where r is the radius of the disk and W is the width. Okay, any questions so far? Okay, this is walking you through it pretty slowly, I think. All right, now to see how to use the volume of a disk to find the volume of a general solid of revolution, consider a solid of revolution formed by revolving the plane region in figure 714, which is here, about the indicated axis. Okay, now what you're going to do, here's x equal a, here's x equal b, and we're taking this curve here. Now let's just call that f of x for right now. Your f of x is your capital R. Does that make sense? That goes from the curve to the x-axis. Now we're assuming that's the x-axis, okay? So f of x minus 0 would be f of x. That's your R. Pi times that R squared times the thickness here, delta x, that would be the volume of that little segment. Okay, now that's not exactly the volume of this curve revolved around the x-axis. That's a lot smoother thing. That to me looks like, I'm sort of hungry, so I think of it as a Hershey's Kiss on its side, okay? So that's what it appears to me. Someone cut off the end here, but otherwise I'd eat the end too, okay? Now, what you've done here is approximate the area under the curve from here to here with this rectangle. And you see this is over the rectangle underestimates this volume, but it overestimates this volume. Okay, so it's going to come out pretty close. So that would be your representative disk, and part of that is inside, part of it's outside the KISS. Okay, because your delta X is finite. Well, if you did that into a series of slices like that, then you would have a series of disks that you're adding together. Okay, that's not going to be exactly the same volume, but it's going to be pretty close. How do we make it closer? Let the delta X get smaller and smaller and smaller until you get to a limit that's going to a dx. And then, where this is a summation of the volumes of these disks, the summation becomes an integral from x equal a to x equal b of your f of x is your radius, so pi times that f squared times dw, or dx, because that was your delta x was the thickness. If you take the limit, it goes to a dx. Okay, so to determine the volume of that solid, consider a representative rectangle in the plane region. When that rectangle is revolved around the axis of revolution, it generates a representative disk whose volume is delta V. That's the portion, the portion of that volume that you have here is equal to pi capital R squared. That's going to be your function value, your y value, the way we were looking at it there, times delta x. Okay, approximating the volume of the solid by n such disk with width delta x. Each of those n disks have width delta x, radius r times your x sub I. So in every one of those, let's go back here, in every one of those disks we'll use this radius for that disk, this radius for this radius for that one, that radius for that one, this radius for that one. So we use the various r sub i's as the radius, and they will be the function values here on the curve for the given x that we're doing. Okay, r of x sub I is basically what we're saying, and that's exactly what they're saying here, the radius r of x sub I. And that produces a volume of solids that will be approximately equal to the solid you're looking for. It's approximately the sum from I is equal to 1 to n, if you have n such disks, pi times your r of x sub I squared. And every time you move up so on, the x sub I changes, so your r changes. Okay, so that's why it's a function of x sub I. Then multiply that by your delta x, because all those are the same thickness. Now, that summation, you can pull the pi on the outside. Pi is just a constant. It's a number. It's not going to interfere with the integration at all. Pull it on the outside, and what you have now is a summation of I is equal to 1 to n of your r of x sub I squared times your delta x. Remember, this r of x sub I was your function value that was ascribing that curve that we were started with. Okay? So that approximation appears to become better and better and better as your norm. Remember, that's what this stood for. That's the maximum value of your partition. However you split up that rectangle, the norm is the maximum delta x that you had there. As that maximum value goes to 0, every one of them is going to 0. In other words, the n's going to infinity. So you can define the volume of the solid as the limit as that norm goes to 0 of the pi that's on the outside now, the summation I is equal to 1 to n of your r x of I squared delta x, and just make that the pi times the integral from a to b, the beginning endpoint, ending endpoint of your r of x, whatever that function value was, squared dx. Now, schematically, the disk method looks like this. Your known pre-calculus formula, and this is what they were talking about before, is your volume of the disk is pi r squared w. That's your individual disk. That's it. Your representative element, which is what they were talking about before, is now a delta V, one portion of that under the curve is pi times that portion, whatever the x of I is at that portion, some representative of x of I, take the r at that value, square it, and multiply it by your delta x. Okay, that takes the place of the w. Okay, well, take the limit of that, the summation of that, and you get the total volume be pi times the summation or the integration from a to b of r of x squared dx. There's your integration formula. Now, after a while, you already got it knocked and you got it figured out, but for now it may seem fairly new. A similar formula can be derived when the axis of revolution is vertical. Okay, and this will be your disk method there. To find the volume of a solid revolution by the disk method, use one of the formulas here. If you're doing your delta x, okay, then you get your y, your r, as a function of x, because if that's your delta x here, you want that to be your integral of integration, and you want the limits to be going x equal a to x equal b. Now, if for some reason you wanted to do horizontal bars, okay, excuse me, it means you got your delta y's here. Now your variable of integration is your y variable. It's going from c to d on the y-axis, and your r of y now is going to be the x value, not the y values. Over here, it was, if that was the x-axis, those were your y values. Over here, if this is the y-axis, this is your x value. If you're going around, so you see, if you do the rotation around the x-axis, do your dx's. If you do the rotation around the y-axis, do your dy's. So you move it around. Now that's for this method, the disk method only. Next section we're going to talk about a different method, and then those things were flip-flopped. Okay, but for right now, that's what you do. And the formula look exactly the same, pi times the integral from whatever your limits are, either in y or in x, times your r of x or r of y, depending on which way you're defining it, squared dx. The pi r squared is your area, and the dy is your height. So that's what you're doing every time. Okay? So here's example 1. Find the volume of a solid formed by revolving the region bounded by the graph. Y is equal to the square root of sine x. Oh, what a fun function. And the x-axis, when you're going from x is going from 0 to pi. Very good choice of limits there, by the way. Okay? And here's why. Because when x equals 0, sine of x is 0, so the square root of 0 is 0. Then it increases until you get down here to pi, and that's where x equals 0. Sine of x is equal to 0 again, so you're only dealing with this. You're not doing anything underneath the x-axis. So you're going to revolve that around the x-axis. So now your function value here is square root of sine x. That becomes your radius of that little rectangle. And guess what you're going to do to that radius? Square it. And the squaring a square root, you lose that. Those are inverse functions of each other. So basically you wound up with something that looks a little like a football, doesn't it? For those who may be ruggers, it may look a little bit more like a rugby ball to you, but whatever. So that's your integration. So let me get my Wacom over here and see if I can do the integration. So what do we just say it was? See if, here we go. We said the integral is going from x equals 0 to x equal pi. And then you have the pi on the outside here. Now that pi has nothing to do with this pi, okay? This is from your formula. The area of a circle is pi r squared. So the pi's on the outside. Your radius here is then this height here. Okay, that's your radius. What is that radius? That's your F value. So it's going to be the square root of sine x but that thing squared because you square it. Ugh, that's ugly. And then you have your dx. That's the thickness. That's supposed to be an x. This that's a really bad x. Okay. All right. So what will that be? The pi on the outside here. Okay, I'm going outside to get it. Okay. Now, let's write this again. X going from 0 to pi. Okay. Well, the square root of sine x squared is just sine x, right? And then you're doing your dx. Does everybody follow? Square root squared is just whatever's under there. All right, so this is going to be pi, the pi that's on the outside there. Why did I put a line there? And I can't erase, or I don't know how yet. Okay, and then what's the antiderivative of sine x? Anybody? Help me. Antiderivative of sine x is minus. Why did that come? Okay. It's just showing up and disappearing. It's minus cosine x. Evaluated from, I don't know why that happened. Nobody else is coming in, but you probably can't see that when that bar comes up there. Okay. And you're going from 0 to pi. Now, this is equal to the pi on the outside there. Now, what is cosine of pi? Does anyone remember? Cosine of pi. By the way, I'm going to put down my minus sign that's in front there. What's cosine of pi? Say that again? No, okay. You're taking the derivative, okay? What is the cosine of pi in trig? Remember, cosine starts at +1, goes down to 0 at pi halves, and then goes down to where at pi? Starts at 1 at 0, goes down to 0 at pi halves, and then goes down how far at pi? You don't like my finger drawing, huh? Goes to -1. The sine of pi, cosine of pi is -1. So you have a minus sign here for that minus sign, but then that would be that makes it a +1. Then you do a minus because you're using this, but you already have a minus. Yuck! Where did that come from? Okay, just out of the blue, that gave me that line. Well, I'm not getting close to the board. Oh, my finger was touching something, I guess. Okay, that's a plus, and then cosine of 0. Anyone remember what that was? I just said it a couple seconds ago. What's cosine of 0? 1. No. Sine of 0 is 0. Cosine of 0 is 1. Okay? Well, 1 plus 1 is 2. Didn't know you'd be doing such high-level math today, did you? So this would just be 2 pi. The volume of that football, you can think of it, is 2 pi. Okay? The length of that is pi, and the volume of it here is something greater than this segment right here. That's a 1 by 1. Okay, so that would be a circle of radius 1, and then they get smaller going this way, smaller going that way, adding them all together, and you wind up with 2 pi. Now that's how we did it. Let's see how they did. Now I wish I knew how to erase. I don't, and I regret doing that now. So let's see what they get. Fortunately, it's very light print, so mostly you can see. From the representative rectangle up here, this one right here, in the upper graph of figure 716, you can see that the radius is your square root of sine x. The radius is that function value, square root of sine x. Okay? And that's what we got here, square root of sine x. Okay? Your formula, the volume for a solid of revolution, is the volume is pi times the integral from a to b, and that was 0 to pi in this case, r squared, that was square root of sine squared, times dx. That's the disk method formula. Okay? And there's your pi, 0 to pi, that was your a to b. Okay? And then the square root of sine x squared, this was square root of sine x squared dx, and that's just simply the integral, pi times the integral from 0 to pi of sine x dx. Now, know your trig integrations. Okay? The antiderivative of sine x is negative cosine x. Why is that? Because the derivative of cosine x is negative sine. So you have to have the opposite sign there. Okay? So this will be pi times the negative cosine x evaluated from 0 to pi. So let's do the upper limit first. Minus cosine of pi. Cosine of pi is negative 1, so minus times minus is plus 1. Then you have a minus because you're doing the lower limit, but you had a minus in front, so minus times minus is plus. Then cosine of 0 is again 1. So this is just simply 2 pi. All right, that's what they got. I forgot to turn the page, and that's what they got in the book as well. Good for them, being consistent. Okay, there was example 1. Any questions on it before we go to example 2? Okay. Now, they're skipping example 2 before they do the washer method. So let's go to our whiteboard and clear this out of the way. All right, move this out of the way. Have to do this all again because we did. Oh, that's in good shape then. Okay, so let me get my Wacom here in place. In example 2, find the volume of the solid formed by revolving the region bounded by the graphs of f of x is equal to 2 minus x squared. Okay. And g is equal to 1. What? Okay. G is equal to 1. G of x, another function of x, is the constant function equal to 1. Okay. About the line, y is equal to 1. Okay. I'm not writing everything in because it's so hard to write. Okay. As shown in the figure. So, thank you for not doing this in the book, as you should have. So let me hold it up so you can see what the figure looks like. Okay, is that it? There it is, I think, isn't it? Yeah. All right. Is that example 2? No, that's example 1. Here's example 2. Okay. Now, this is a parabola, 2 minus x squared. There it is. Okay. Symmetric about the y-axis. Okay. And that's what we're revolving. Only we're revolving around the line y is equal to 1. Where is y is equal to 1? That's that line there. Okay, you see the graph. It would have gone on down to plus or minus 2 or square root of 2 or somewhere down there, but we're only doing to 1. y is equal to 1, or g of x equal 1. And then we're using that same y, and that's what we're revolving around. I hate that I have to hold this up like that, but that's so much better than me drawing the picture. Okay? So, oops, I keep forgetting and using my finger on the Wacom. Okay, so what are we doing? We're doing from the graph of that parabola, 2 minus x squared minus 1, because you're subtracting off the g. That's the part we're doing. That's your height of the rectangle. The f minus g. That's the height of the rectangle. And then you're revolving that around that same line, y is equal to 1. Okay? So that's our setup here. Let's see if we can figure out what it is. Okay? The volume then would be, you always have your pi when you're doing this disk method. Okay? And that'll be the integral of your r. Your r here is f minus g. You're going from f down to g. So that would be 2 minus x squared minus 1. Okay? 2 minus x squared minus 1 would just be 1 minus x squared, right? 1 minus x squared. Okay. Now, we didn't do anything to figure the limits of integration. So basically we set this equal to that. Let's go over here and do that. Okay, 2 minus x squared is equal to 1. That's supposed to be a squared there. I'm going to move to the squared to the other side and make it x squared. And then I'll subtract 2 from both sides as well, and that will be a minus 1, and that's going to be equal to 0. What are our limits of integration then? This factor says x plus 1 times x minus 1. And that's equal to 0. Okay. This gives us x equal minus 1. For some reason, it's not working too well. X equal plus 1. I don't know if I'm hitting the board too hard. I don't know why it keeps flashing like that. So those are your limits of integration. Okay? Remember, this is a parabola centered on the y-axis. So we don't have to do this. We can take the volume from 0 to 1 and double it. And that's exactly what we're going to do. So what I'll do then is come out here and put the 2 here, and then just do our limits from 0 to 1. And then you'll have your dx. Okay. Now, so this is going to be 2 pi. Antiderivative of 1. Somebody help me here. It's the antiderivative of 1. Say again? Yes, 1x or just x. Okay. Antiderivative of x squared. Hint, it has an x in it. X cubed over 3. I hope y'all know these, right? Okay. And then we're going to evaluate that from 0 to 1. Okay. So here's a 2 pi times. Okay. When you plug in a 1 here, that gives you a 1 minus 1/3. Everybody agree? And then I'll plug in the zeros. Okay, I'll volunteer for that. 0 minus 0. Okay, got it done. Well, obviously, this is 2 pi times 1 minus 1/3 is 2/3, right? Please say that math was easy. And 2 pi times 2/3 would be 4/3 pi. That should be our answer. Okay. Oh my goodness. How did I botch it up? Oh my goodness, of course. I got the radius. Sorry about this. Let me get my eraser activated here. Big time. I got so carried away. Okay. I hope, nope, my eraser's not activated. Come on, eraser, get activated. Okay, there we go. I forgot a very important part. Your area of the disk is pi r squared. I got so focused on the r part, I didn't square it. Okay, so let's go back up here. Okay. Sorry, we were supposed to square the radius. The radius was 1 minus x squared. We got that right, but we didn't square it. Sorry about that. Okay, so that volume is then going to be 2 pi. That part was right. Okay, we'll still keep the integral here, 0 to 1. Okay, now square 1 minus x squared. Can anyone do that sort of in your head? 1 squared is 1. When you're squaring a binomial, square the first term, 1. I could do that one. Twice the product of the two. Well, that would be a minus 2x squared. The product of those two is a minus 2x squared, and then plus the square of the second term, and that would be x to the fourth. Okay, and then we'll do our dx. Now, you probably could have done that with a reverse chain rule or something. So much easier to do it this way. Okay, so that's going to be our 2 pi times. Now, go back and try this again. What's the antiderivative of 1? Anyone remember? Please say yes. X, perfect. Minus, and what's the antiderivative of 2x squared? Okay, 2x cubed over 3. Don't forget your 2. Okay, plus, what's the antiderivative of x to the fourth? X to the fifth over 5. Okay, and now we'll evaluate that from 0 to 1. Okay, remember we're doubling, and that's why we're able to get away with that. That's a 2 pi. Okay, when you plug in a 1 for the x, that first x just then becomes a 1. Minus, plug a 1 in for x, cube it, you still got 1, that would be 2/3. Plus, plug a 1 in for x, you get x to the fifth is 1, so 1/5. Oh, I'll do the 0 part. That's 0. Okay, that's why I love doubling and doing. You can only do that when it's symmetric, so don't get carried away with it. So what's this going to be? 2 pi times. Now let's get everything in terms of our least common denominator. What is the least common denominator? 15, right? So this will be 1 is 15/5. 15/15, I'm sorry. Okay, minus, how many 15ths is 2/3? Isn't that 10/15? And how many 15ths is 1/5? Pretty sure that's 3/15. Okay, and when you add all those together, you get 2 pi times 15 plus 3 is 18 minus 10 would be 8 15ths, I'm pretty sure. Why did that happen? Okay, it's 8/15ths. Okay, and 2 times 8 is 16/15ths times pi. Whew, goodness. All right. I'm used to writing where I'm looking. I'm having to write on a pad while I'm looking at the screen. It takes some getting used to. All right, any questions on that one? Sorry about forgetting to square my radius. Don't forget to square your radius. I was just doing that as a object lesson. Okay, any questions before I leave this? Oh, I have to move the Wacom out of the way to use my keypad. Okay, so let's go back to the screen share. We'll go back to the PowerPoint 17.2. Okay, go from current slide, which we finished example 1. We just did example 2. Now we're ready to move to page 457, example 3. Okay, now we go till 225, so we got plenty of time. So let's look at the washer method. Okay, the disk method can be extended to cover solids of revolution with holes by replacing the representative disk with a representative washer. A washer is a disk with a hole cut out of it. Almost think of a donut if you're into food, but you know, it's a one-dimensional donut, you know. All right. The washer is formed by revolving the rectangle about an axis, usually not part of the rectangle. So you see, here is where your rectangle is, from here to there, but you're revolving around an axis there. So the part in here has nothing revolving, and that leaves you the hole that you see down here. So now we get that rectangle up here revolves around this axis of revolution, and that gives you a washer. Now that's a pretty thick washer too. Thick this way and thick this way. If little r, which is your distance above the axis of revolution on the bottom part, and big R is the distance above the axis of revolution for the upper part, that then forms, if little r and big R are the inner and outer radii of the washer, respectively, meaning little r is the inner and outer R, big R is the outer, and W is the width of the washer, then the volume of that washer is pi times the difference between their squares. Now, why the difference between the squares? Not just the square of the difference. No, that wouldn't work. You have to do the disk that's out here, the big disk, and then subtract off the little disk. So that's why you have to square both of those. So this is the shorthand way of writing it. Okay? To see how this concept can be used to find the volume of solid of revolution, consider a region bounded by the outer radius r of x, inner radius little r of x. But this time, these are not just fixed numbers. This is a function, and that's a function. Okay, so now we got the difference between two functions, but not finding the area like we did before. That would be summing all these together. We're finding the volume when they revolve around some other axis that's not part of the little r or the big R. That's the axis down here. Okay, so that's going to give you something that looks like a Christmas tree stand. Okay, with a little bit of imagination. It's kind of a big old Christmas tree stand. Big hole up here, but not very solid here. So it's this area here revolved, and why they didn't draw it up here, I don't know. Drawn here, circled around there. So that's the volume of revolution. It's a very thin disk here, a washer here, thicker here, and then thinner here, because out here you're very, very thin again. Okay, that part is the only part being revolved around. This is a thicker part, and there it gets thinner at the edge too. So there's your schematic of your solid of revolution, okay, when you get a washer method. If the region is revolved about the axis of revolution, which is not part of the shape itself, then the volume of the resulting solid is, again, the pi is on the outside, and then the radius squared of the bigger washer times its dx minus the radius squared of the little washer, the inner washer, times its dx. So you're subtracting the two volumes, the whole volume from the solid volume. Okay. Note that the integral involving the inner radius represents the volume of the whole. It's subtracted from the volume involving the outer radius, which would have been the entire disk if you had a disk. Okay. So here's example 3, bottom part of page 457, I think it is. Yeah. Okay. Find the volume of the solid form by revolving the region bounded by the graphs of y is equal to the square root of x and y is equal to x squared about the x-axis. Okay. Now, what you have to do first is figure out what the limits of your integration is going to be. Well, where is this y equal to that y? So that's the first thing we're going to do. And let me get my Wacom back up here, and let's do that. So you set the square root of x, I must be hitting on something, okay, equal, where's, oh, there it is, okay, equal x squared. Well, I think you can almost just look at that and tell where those are going to be equal, okay. What you can do is square both sides, okay, that would be one way to do. Realize when you do that you may be introducing some extraneous roots there. That would be x equal to x to the fourth. So in other words, x to the fourth minus x is equal to 0 when you subtract x from both sides, and this would be x times x cubed minus 1 when you factor, and that's equal to 0. And then when you factor that yet again, that would be x times, this factors as x minus 1 times a factor that won't produce anything. X squared, I don't know if you remember that, x squared plus x plus 1. Now that's never equal to 0, ever. So your two places this equal to 0 is x equals 0 and x equal 1. And of course, those are the two places where those equal. The square root of x, oh, I keep forgetting. The square root of x starts at 0, 0 and goes up to 1, 1 and keeps on going up this way, where x squared starts at 0, 0 and goes up much more slowly until it hits 1, 1 and then exceeds it and keeps going like this. Okay, so obviously this is the region of intersection. Okay, so your square root of x is on top, x squared is on the bottom. Okay, so we need to find the volume. So let's get my Wacom back where it belongs. Okay, hopefully I won't be making any noises this time. And your volume would then be the integral from 0 to 1. I like those limits. Okay, your pi is on the outside. I want to go out and get it. Okay, and it's your square root of x squared, which would just be x minus x squared squared, which would be x to the 1, x to the fourth. That looks a lot like what we just had over here, but in reversed order. This is what you're integrating dx, because your little wedge here, your little rectangle, has a thickness dx. The difference between this squared and that squared when you revolve it around the x-axis. And that's something sort of neat here. They use the x-axis, not anything else. Oh, I can't get up there. Okay, sorry. Okay, so let's do that integration. I can do the pi, it's out front there. Okay. Now, what's the antiderivative of x? Somebody. Anybody. It's x squared over 2 minus, what's the antiderivative of x to the fourth? X to the fifth over 5. Evaluate that from 0 to 1. Okay? Now, I'm going to come down here near the bottom somewhere and write our answer here. The pi is pi times, when you plug in a 1, 1 squared is 1, so it's 1/2 minus, and then plug in a 1 for the x and raise it to the 5th power, it's still 1. That's 1 over 5. And when you plug in the zeros, you get absolutely nothing. Okay? So this will be pi. Least common denominator here is 10. So that will be 5/10 minus 2/10. Okay? And that would be 3/10 pi. All right. By the way, that's something just awfully close to 1, because pi is 3.14 times 3 is 9 point something another, getting pretty close to 10. So 10 over 10, let's see what they got. 3 pi over 10. This time they got it right. I'm so proud of them. Okay. All right. Any questions on that? Well, they're going to do it, so let's proceed and see how they do it. So let me get my Wacom out of the way here, and we'll go on to this. In that figure that you saw that I held up, you can see that the outer and the inner radii are as follows. The outer radii, the big radius is square root of x. The little radius is x squared. That's because we're only traveling between 0 and 1. If you were outside there, then the outer radius was going to be x squared and the inner radius would be square root of x. That's if you're beyond 1. We're not there. That doesn't make a closed shape. This one did. Okay? Integrating between 0 and 1 produces the volume would equal to pi times the integral from a to b, in this case 0 to 1, of your outer radius squared, that's going to be x, minus your inner radius squared, that would be x to the fourth, dx. Okay? So that would be pi times the integral from 0 to 1 of square root of x squared, which is x, minus x squared squared, which is x to the fourth, dx. And that would be the integral from 0 to 1 of x minus x to the fourth dx. And then the calculus part's so easy, isn't it? Setting it up is a major work here and visualizing what's going on. But the calculus then is pretty easy. That would be pi times x squared over 2 minus x fifth over 5. Evaluated from 0 to 1. And that gives you 3/10 pi. And again, they did the easy part, and the harder part, which is doing the least common denominator, just brushed right on through that. Okay. Any questions on that before we move to whatever is next? All right. Looks like example 4 is next. Let's see if they do it. Okay. In each example so far, the axis of revolution has been horizontal, okay, and you have integrated with respect to x. In example 4, which is coming up next, the axis of revolution is vertical, so you're going around it this way, so you're going to want to take your washer thicknesses as dy, integrating with respect to y. In this example, you need 2 separate integrals, well, we haven't gotten there yet, to compute the volume. So let's see what the integral is. Find the volume of a solid formed by revolving the region bounded by the graphs of y is equal to x squared plus 1. That is a function of x. And here's what it is, x squared plus 1. That's the parabola going up like this. Y is equal to 0. That is your x-axis down here. X equals 0. That's the y-axis here. And x equal 1. That's this line right here. Okay? About the y-axis. So this is going around the y-axis here. Now, I don't like the way they've phrased this. Find the volume of the solid form by revolving the region bounded by the graphs of y is equal to x squared plus 1. That's that right there. Y is equal to 0. That's your x-axis. Y is, oh, I misread it. X equals 0 is your y-axis, and x equal 1. Okay, I thought it was this line here. That's y is equal 1. X equal 1 is this one here. That gives you an endpoint here. Okay, this is making more sense. For some reason, I wasn't looking at this. I was looking at this. It said x equal 1. It's y is equal to 1. That's that line right here. And we're going to revolve that around the y-axis this way. So you're going to get then, I don't know what to call that. That's a right circular cylinder, but you've sucked in the top, so it forms a paraboloid. You don't even know what that is yet. Maybe you do. But anyway, so you have an indentation in the top, okay? A pretty major indentation in the top, okay? And you're going to revolve that around the y-axis, okay, the y-axis. Now, here's why you have to have two integrals. But actually, you don't even have to integrate this one. You know this is going to be a right circular cylinder of height 1, okay, and radius 1. So you can do that in your head. The area of the base is pi times 1 squared, which is pi, and then you multiply that by the height, and that's pi, 1. So it's just going to be pi. So you don't have to do another integration down here. You can just do that one based on something you already know. This one, though, because you're revolving around the y-axis, okay, and you're wanting to take delta y, you have to get this expression in terms of a function of y, not as a function of x. So the first thing we're going to do there is that, okay? So we're taking this expression here and solving it for x. So the first thing we're going to do is subtract 1 from both sides. So that gives us a y minus 1 is equal to x squared. Agreed? Must be hitting something. Okay. Now, then we want to solve for x. So x is equal to, I don't know why that line went out there, the square root of y minus 1. Okay. Now, technically we ought to say plus or minus. But remember, this x is only representing a radius. So the radius that we have here, that's your little r here, and that's going to be just the positive square root of y minus 1. The outer limit is just going to be 1. Y is x equal 1 minus x equal square root of y minus 1. So that's going to be the only integration we really have to do. Like I said, you can do this one just by knowing the formula for the volume of a right circular cylinder. Pi r squared h. The radius is 1, so that's going to be pi times 1 squared is 1, so that's pi, times the height is 1, so pi times 1 is pi. So that's going to be the base down here. So I'm going to write this volume here. V for the base here is going to be pi. Okay. Now we're going to come up here and do this one. Okay. So let me see if I can find the room to do it. This will be the integral And you remember you got your pi out front, okay, because pi times the big radius is going to be 1, and 1 squared is 1. So that's going to be 1 minus, and your little r here, your x on the inside, is the square root of y minus 1. What's that? That's squared. You got to square it, remember? Minus that squared would be minus y plus 1, because minus a minus 1, okay? Okay, because when you square that, you get y minus 1, and then, so this gives you, oh, I forgot my dy, that's your thickness, and I think I'll write it down here. This gives you pi times the integral of 2 minus y dy, okay? And this is going from y equal 1 to y equal 2. We don't have that fun 0 there anymore. I forgot to write them in here. I should have 1 to 2, because we're only doing with this portion up here, y going from 1 to 2. We've already got the volume of the base. So this is the volume of your indentation part, okay? So it's going to have a pi in it. And then the antiderivative of 2 is 2y minus y squared over 2. We're going to evaluate that from 1 to 2. Okay, so that's going to be pi times, when you plug in a 2, that's going to be a 4 minus 2 squared is 4 over 2 is 2. Now you got to plug in do a minus here. Minus 2 times 1 is 2. And then you got a minus times a minus, which is plus 1/2. And here's James. Good deal. Let me let him in first. I've got to get my things out of the way here. Oops, get out of the way there. All right, James is coming in. Okay, say that again. Okay. All right. Now, James, we're on in Chapter 7, Applications of Integration. We're in 7.2, which is Volume, the Disk Method. Okay? And we're on page 458, Example 4. We're almost through with Example 4. We're getting awfully close. Okay, let me do a quick rehash of what we have here. We have the volume of this shape. Here is your y squared, y is equal to x squared minus 1. That's a parabola going up like this. Y is equal to 0, which is the x-axis. X equals 0, which is the y-axis. And x equal 1, which is your boundary over here. We're revolving this around the y-axis, and we're using what they call the washer method. Now the part down here is just a solid rectangular cylinder, right circular cylinder, and its volume is pi times its area times its base. Its area is a circle of radius 1, so it'd be pi r squared, and radius is 1, so that'd just be pi times the height, and the height is 1. So that's just going to be pi. So the volume of the base is pi. We've already done that, not using calculus at all. But we use calculus to get this part. But first we had to get this expression in y as a function of y, as x as a function of y. So we subtracted 1 from both sides and then took a square root, and we got this. We only use the positive square root because our picture here shows you're going from the outer radius of 1 minus the inner radius of square root of y minus 1. Okay? The formula says square the outer radius, 1 squared is 1, minus square the inner radius. The inner radius here is your x, and that would be the square of square root of y minus 1 is y minus 1. But when you're subtracting it, which you're doing here, this minus this, then that gave you minus a y plus 1. that gives the integral of 2 minus y dy evaluated from y is equal to 1 to 2. Okay, and we just did the integration and we got this. We just plugged in the values here and I think we got that, so let's do it. It's hard to see. This is a 4 minus 2 minus 2. That's minus 4. That adds to 0. So you just get a 1/2 pi. So this part down here, whoops. I have a new Wacom tablet. I'm not used to doing it. Okay. So that's going to be pi over 2. Okay. But this was pi, and we add to that pi halves, and we get 3/2 pi. That's the total volume. And I don't know why it puts those horizontal bars like that, but it does sometimes. I must be hitting something I shouldn't. And that is what they got in the book, 3/2 pi. Okay? So that's how we did it. Let's watch how they did it. Okay? For the region shown, the outer radius is simply r equal 1. And that's what we saw here. Outer radius, r is equal to 1. You're going from here to here. Outer radius is 1, all the way up and down. Okay. There is, however, no convenient formula to represent the inner radius. Okay. When you're between 0 and 1 on y, the inner radius is 0 because you don't have a washer, you have a disk. But when it's between 1 and 2, y is between 1 and 2, r is determined by this equation. So what we had to do was subtract 1 from both sides and then take the square root of that. So your r, or your x, was equal to the square root of y minus 1. Okay, so that's your little r. Capital R is 1, little r is square root of y minus 1. Okay, so we have two different things. Your inner radius is 0 from 0 to 1, so you just have a washer, a disk, and from 1 to 2 you have a washer with this as the inner radius. Okay, why they're making it so complicated, I don't know. So using that definition of an inner radius, you can use the two integrals, which is just ridiculous, but it's right. Pi times the integral from 0 to 1 of y, and that's just 1 squared minus 0 squared. It's just 1. So that's just going to be 1. This will be 1. Integrate that, you get y. Y value from 1 to 0 is 1. Multiply that by pi, you get pi. So that was easy. Okay. The second one, though, pi times the integral from 1 to 2, is, again, your outer radius is 1. So 1 squared is 1 minus the inner radius squared. The inner radius is y square root of y minus 1, and when you square that you just get y minus 1, and when you subtract it you get minus y plus 1. So they did all that work just to get this plus this, and that's exactly what we got. They sort of left off the step that had some complication in it, and you had to figure that out for yourself, but we've already done it, and that's correct. And this will just be, oh boy, they just beaten this to death. Pi times the y evaluated from 0 to 1, that's just going to be 1 times pi is pi. We had already done that. Okay, and this is going to be pi times 2y minus y squared over 2 evaluated from 1 to 2, which is what we got also. And this is just pi, and this is pi times, when you put the 2 in for the y, you get 4 minus 2 squared is 4 over 2 is 2. And then when you do the minus the lower limit, that would be minus 2 times 1 is another minus 2. And then minus and minus makes this a plus 1 over 2, which is 1/2. These first three cancel out to be 0, and you just have 1/2. So it's pi plus pi halves equal 3/2 pi. All right. And that's what we got. Any questions on that? All right, that was example 4. Let's move on to, note that the first integral represents the volume of right circular cylinder of radius 1, height 1, which is what we said from the very beginning. That portion could have been determined without using calculus, which is what we did. Okay. Now, they're skipping example 5. Oh yeah, they're skipping example 5, and then this is picking up at the bottom half of page 459. So let's go back a slide and do on the Wacom example 5. And by the way, even if you don't have this book, you can go to larsoncalculus.com for an interactive version of this type of an example. Okay, and here's what we've got. I'm going to pull it here in my lap so I can read it more easily. I've got so many wires all over the place here. I've got headphone wires, I've got Wacom wires, I've got wires. A manufacturer drills a hole through the center of a metal sphere of radius 5 inches. Okay? Now, I don't want to have to draw this, so I'm going to hold it up in case you don't have a book so you can see what they're talking about. Okay, there's a sphere of radius 5, but he drills a hole through the middle of that sphere. Okay, they show it being horizontal, which is fine. Okay, so that's the picture. I'm not going to draw it. You get that in your head. Okay, now, where's my pen? There it is. Drills a hole through the center of a metal sphere of radius 5 inches as shown in the figure. I'm going to have to draw it, am I not? The hole has a radius of 3 inches. What is the volume of the resulting metal ring? Yuck, I'm going to have to draw this. Okay, so let's go to yuck. Oh, how did that happen? Okay, I'm not sure where we went there, but we're going to the white page. I don't know where we were just then. It looked like the white page, but it wasn't. I'm going to clear this. This, by the way, is the last example we did on the drawing. So let me clear that out of the way. Okay. Now, using the Wacom, this is so aggravating. I think it's the Wacom must be hitting keys here. And okay, let me see if I can lay it down gently here. There's a part of me that wants to move the computer out of the way, but then I'll be writing here and looking over to the right to see what I'm writing. So this makes it just a little bit easier. Okay, but I'm going to have to try to draw this. Okay, now I'm starting to draw on the screen. Okay, here is what it's going to look like. No, actually here I'm going to do something different. Oops, that's not it. That's what I want. Okay, I'm going to draw. I'm going to erase. Okay, I'm so sorry. Okay, it's still not working. There it is. Erase this mess. Okay, go back to this. Okay, now here's my vertical axis. I'm going to make it as close to vertical as I can. I didn't do a good job of that. Let me see if I can straighten it up just a tad here. I can't get it to. Okay, here we go. Okay, I'm going to leave it like that. And here I'm going to draw, if I can, my horizontal axis. And I don't know why it went to that. I haven't figured out this whiteboard yet. It does whatever it wants. Okay. let's just say that's supposed to be a horizontal axis. It's nowhere close to horizontal, is it? I kept trying to bring it down and it kept jumping back up. So let's go down with it. Okay, that's as close to horizontal as I can get, I think. Okay, now let's tick off a few points here. This is going to be pretty pathetic. 1, that's supposed to be horizontal. 2, 3, 4, and 5. This will be 1, 2, 3, 4, and 5. This will be 1, 2, 3, 4, 5. Obviously I can't draw straight lines, but I'm not really trying that hard now. 1, 2, 3, 4, 5. Now that would be our sphere if I drew the circle for that. So let me at least do a cursory attempt at what that sphere would be. Oh, I can't use that, can I? I've got to go back and use my curve. Oh. I'll use that one. Now where do I start it? I think I start it here. No, that's not the place to start. Okay. Let's go back to the drawing. Okay, I think I start somewhere like here. No, that's my eraser. I thought I clicked that off. Uh-oh. Okay, I think I've got it back. All right, now this is my attempt. No! This is so aggravating. Being left-handed, this is not set up for left-handers. Okay, let's try this again. Starting right about here. I may stop a minute. Let me see if I can get this to do. Okay. There's a circle. Okay. There. Now, it's not perfect, but it's sort of like a sphere, okay? I want to move the whole thing to the left a little bit, but I'm not sure how to do that. So I'm going to stop right there. Okay, let that be it. Okay, now what we're going to do is cut a hole of radius 3 in that. Okay, so I'm going to, radius 3 would be here. Okay. No, now that's doing what I wanted to do before, but I didn't think I could do it easily. Okay, stop there. Okay, now let's go back up here and do something else. I think I do want to do a circle of radius 3. So let me try this and see what I can do. Okay, there's my cross-sectional area of radius 3. Now this is it's going to be sort of crazy, but let me try that same thing right here. Now it's not doing it. Uh-oh. Okay, and go back and see if I can do one over here. All right, those are all approximate. Okay, now what we're going to do is come up here. not that, not that. This is there, that one. Okay. Now, yuck. Okay. I think I just found out how to erase something, whether I wanted to or not. But let me see if I can just do it here. Okay, that's supposed to be radius 3. And why it makes me come back and do this again. And this should be radius 3. Only I want that whole thing to come down to right about there. Okay. Now if you can sort of figure what I've got there, there is my hole of radius 3 cut in my sphere of radius 5. Now it's pretty ugly, I'll admit that. Okay. Now, why take that much time to do this? Okay. Now, what we're trying to do is get the volume of the resulting metal ring. Okay. Now, I think I'll go now to my curve here. Okay. Now, maybe not. Okay. I think I'll do one more construction line here. Okay. This one more construction line here I'm going to do, I thought I was going to do, is this line here. Okay. Now the reason I did that line is that hopefully you see, okay, here are going to be my little rectangles. Okay, and that's going to be my dx. Whoops, I gotta get my draw back again. Okay, this is going to be dx, the width there. Okay, the height is going to be the y value minus the y of the outer circle here minus the y of the inner circle. Okay, well, the y of the outer circle is going to be a circle of radius 5. Okay, hope you see that. Okay, the radius of the inner circle is going to be 3. Okay, because this was 3 here. Whoops, I'm writing on the, okay, this is 3 here, and this curve up here is, okay, time out just a moment. If I had had this centered at the origin, which I wanted to have, but it isn't quite there, but close, okay? The left-hand side over here is going to be exactly like the right-hand side here. So I'm going to do everything from 0 to whatever my limit on x is out here, okay? That's what I'm going to do, and I'm going to double, okay? So what we need to do first is find out what this x value is. And that's why I drew this line, because this line is the radius of the sphere, which is 5. This line is the radius of the cylinder, which is 3. So this up here has to be the square root of 25 minus 9, which is, of course, hopefully you see that. What is that? Yuck. Quit doing that. Okay. Oh, I know what I'm doing. I'm hitting it with my hand. Okay. This is equal to 25 minus 9 is 16, square root of 16. Why is that not there? I've drawn it twice now. Okay. This is 4. Okay. So, and sure enough, my graph even looks like it's pretty close to 4. Surprise, surprise. Okay. Now, so our x's are going from 0 to 4. We're doubling it. So let's see what we've got then. The volume is equal to twice pi times the integral from 0 to 4. Okay, the outer thing here is the area of that circle. Okay, and if you're doing it in terms of x, which we are, this would be the square root of 25 minus x squared. Okay, that would be, oh man, I messed that up. Trying to clean it up, and it just got worse. Okay, let me erase some of that. Okay. It's terrible. I have to focus so much on the technology, I can't focus on the calculus. Okay. That's going to be the outer radius. Okay. This is your, I keep wanting to write on the screen. See, before that's what I was able to do. Here is the outer radius, R. That capital R is the radius of that circle. That's the y value, and the circle is x squared plus y squared equal r squared, which is 25. Maybe that would be helpful to write somewhere here. X squared quit. Okay, come on, get off that. Okay, quit. Okay, maybe I can get back to writing again. Okay, that is x squared plus y squared is equal to 25. And we want the y value, which would be y is equal to the square root of 25 minus x squared. Okay, that's where we got that. But that is your outer radius r, so let me find it here and write that as your capital R. But we want r squared, so that's going to lose the square root. So I'm going to write the square in there, okay, minus the inner radius. Well, the inner radius is 3. This is your inner radius r, 3. Well, 3 squared is 9, so that's going to be 9, okay, and that's going to be what we multiply by dx. Okay, there's the height here minus the height here. This square root of the height here squared minus the height here squared. I'll get this out of my lap because it's heavy and it's hot. Okay, okay, there's our integral that we're trying to do now. Now if I can get my pen to show up somewhere here, there it is. Okay, so this is equal to 2 pi times the integral from 0 to 4, okay, of, when you square this, you just simply get 25 minus x squared minus 9, and that's dx. Okay, fairly simple. I have to be slow when I draw on this, I guess, because it doesn't accept it if I go too fast. 0 to 4 of 25 minus 9 is 16 minus x squared dx. Okay, now hopefully you can do that integral. 2 pi times antiderivative of 16, 16x minus x squared. Antiderivative of that is x cubed over 3. We're evaluating that from 0 to 4. I don't like to do all the talking. I wish y'all would be doing talking, but I ask questions and I get some responses, but I almost have to yank it out of you, but then I feel like I'm not covering material fast enough, so sorry if I'm going. Okay, 2 pi times, when you plug 4 times 16, that's 64, minus, and 4 cubed is 64, so 64 thirds, and then I'll do the 0 part, that's just 0. This will be, here's what I'm going to do. Hopefully it's okay with you. I'm going to pull the 64 out. 64 times 2 is 128 pi times, and then what you have left over is 1 minus 1/3, so that's 2/3. Okay, and that's equal to 2 times 128 is 256 thirds pi. That's the volume, I hope. Yes, that's what they get. Oh, I didn't even realize it. They gave all these things in terms of inches, so this would then be cubic inches. And really, being a physics by nature, where is it? There it is. This is cubic inches. (256 thirds pi cubic inches). And by the way, just to get an idea of how big that is or how small it is, pi is just a little over 3. So this is something a little over 256 cubic inches. I would say probably 260, 265, 270, something like that. They don't even do it to show. But anyway, was that someone trying to get in? I just saw the thing go down. I wasn't paying attention. All right. Any questions on that problem? I know that's sort of an ugly, awkward problem, but did anything out there make any more sense? I'll put you all asleep, okay? Really? Okay. All right. Let me do a couple things here. First, I'm going to move this taskbar a little out of the way because I kept dragging it downward by not meaning to, but I did. Okay. And let's go back to, the PowerPoint. Okay, and we'll go back to current slide, which we finished example 4. We just finished example 5. So now we're moving to the bottom half of page 459, solids with known cross sections. Okay, we got about 24 minutes left, so don't let me run over, please, folks. I've got another class starting at 2:30. Solids with known cross sections. Okay, with the disk method, you can find the volume of a solid having a circular cross section whose area is pi r squared. Okay, most of these are circular cross sections. This method can be generalized to solids of any shape as long as you know a formula for the area of the arbitrary cross section. Now this gets into some, it can get into some sort of tough calculations here. They're really fairly simple theory-wise, but getting the actual values sometimes is a lot harder. Some common cross-sections are squares, rectangles, triangles, semicircles, trapezoids, things such as that. And the more you think about it, those areas may not be so well known to you, but we'll run into them. So here's volumes with solids of known cross-sections. For a cross-section of area A of X, so the area is dependent on X. Okay, I'll show you what that means in just a second. Taken perpendicular to the X-axis. Perpendicular to the X-axis. This is perpendicular to the X-axis. Okay, So for a cross-section of a known area A, now we don't know the area A yet, but we'll get to it in a minute, taken perpendicular to the x-axis, the volume would be from x equal A to x equal B of that, the integral of that from x equal A to x equal B of that area times your dx. The dx is going to be the thickness of that. This would be the known area. Okay? If it's taken A of y perpendicular to the y-axis, then you go from C to D, whatever you were on C, to D, and you take your known area, the volumes of the known area, times your thickness here. So basically you're summing up the areas from here to here of those known volumes, known shapes, or from base to front, okay, that known shape. All right. Now, in this one that they're showing here, I sure don't know that shape very well at all, okay, because it has a curved top here. These are straight lines here and here. That's a curved straight top. That's not an area I have in my repertoire. However, this one, at worst, that's a rectangle, okay. Almost looks like a square. It looks like a square back here, not far from being a square here, but at worst it's a rectangle. That's the length, or that's the length, and there's the width, okay. Hey, I know the area of a rectangle, length times width. The length here is your twice the x value, okay. The width here, the length here is your function value, whatever that function is there, and the width is twice the x value. That's how we proceed. I would not try to do this one at all, not with this shape, because that's a curvilinear thing. Not going to mess with that one. This one, that forms a rectangle. The height of the rectangle is your f value. Your length of the rectangle is twice your x. That's the one I would go for. Okay? Even though it is a dy. So let's do, here's example 6, triangular cross-sectional cross-sections. Find the volume of a solid shown here. Thank you for drawing it. Okay. The base of the solid is the region bounded by the lines f of x equal 1 minus x over 2. Okay. That would be this f value here. 1 minus f over 2. This is the y. Yeah. The y is, 1 minus x over 2. That looks right. Because this, you have to sort of flip this up a little bit, like this to look at it. And the y-intercept is 1, 0, 1, and the x-intercept would be 2, 0, because you plug a 2 in here, you get 2 over 2 is 1, 1 minus 1 is 0. Okay, so yeah, that's the this line right here, f of x equals that. Your g of x over here is minus 1 plus x over 2. And again, look and see if these points fit. When x equals 0, that's on the y-axis here, g is minus 1. Sure enough it is. That's the y-intercept. And on the when x is equal to 2, then this gives you a 0, because you got minus 1 plus 1 is 0. So that sure enough gives you that shape. And x equals 0. X equals 0 is the y-axis back here. So you're not going anything beyond that backwards. Okay. Now, that gives you your base here. Okay. That's the sort of dark blue here. That's the triangular base formed by that line, this line, and x equals 0 back here. Okay. Now, for that triangular base, we're going to draw it like this. Flip that up like this. Okay. There's your triangular base. Now, the length here, and that's all you're dealing with here, the length of the base of that triangle right there, that length of that base is from F minus G. That's all it is, F minus G, okay, is the length of that base, which frankly is twice the length of F minus 0, because this is exactly the opposite of that. So I would go with that, okay, the length would be twice 2 times F, okay, now that's the length. The cross sections are perpendicular to the x-axis. They're equilateral triangles. Now, they didn't say anything about that here. They tell you down here, the cross sections perpendicular to the x-axis are equilateral triangles. That sure looks like one there. That kind of looks like one back there too. Sure enough, they are. So in other words, this base here, which we just determined would be twice your f of x here, okay, that base here is also the length of this slant side and that slant side. Well, the height of that triangle would be square root of 3 over 2 times that length, because that is what you get. But we'll get to that in a minute. Let's not get ahead of ourselves, okay? So the base and the area of each triangular cross section are as followed. Here's the base. It's this length, what was that, f of x minus g of x, and that's just twice this. So sure enough, it's 2 minus x. So there's the length of the base, okay? Now, the area is 1/2 the base times the height, okay? And like I said before, and they sort of left this off here, your equilateral triangle, this side here is, let's call it, that's 1/2 the length of that base, okay, that part. This part is exactly okay, trying to think the best way to say that. This length here is exactly the same as that length there, okay? It is exactly the same as that length there. That's what it means to be an equilateral triangle. So if you do your perpendicular from the vertex here down to the x-axis here, that splits this exactly in two. So 1/2 the base, the height here is, okay, these are not the right numbers, but I'm going to use them. Let's just say this is length 1, that's length 2, and this would be the square root of 3 over 2. Okay, why? Because this is a 60-degree angle here, and the height here, well, let's do it this way. 1 squared plus 2 squared would be 5. No, that's not what I want. Yeah, and no, I'm saying 1 squared minus 2 squared minus 1 squared would be 3 squared, and the height here would be square root of 3 over 2. Okay, that's what the height of that triangle is. That's what they're using without telling you how they got it. So it's 1/2 the square root of 3 over 2 times the base squared. Now, why the base squared? 1/2 the base times the height. Well, the height was the base times square root of 3 over 2. And then the base was the base. So it's 1/2 square root of 3 over 2 times the base times the base. So that's why you get that. And again, I thought they did a lousy job of illustrating that. They could have done much better, I thought. Okay, but that is indeed true. That's the area of a slice of that equilateral triangle slice. Okay? Now what is the base? The base was 2 minus x, so it'd be the square root of 3 over 4 times the square root of 2 minus x squared. That's the area of every one of those slices. And your slices are going from x equals 0 out to x equal 2. Okay? So that's what you're integrating from 0 to 2. The volume is the integral from 0 to 2 of that area times the thickness. Okay? And the area is, it's going from 0 to 2 of square root of 3 over 4 times 2 minus x squared dx. We'll pull that square root of 3 out of 4 out front and then square your this way. Okay. One way you could have done it was squaring this and then doing your integration that way. How they chose to do it was sort of reverse chain rule type thing. Let u equals this, u equal 2 minus x, du would be minus dx, okay, and then this would be u, a minus sign up front, u squared du, and u squared, the integral of u squared du is u cubed over 3, and you go back to and put in the x's in there, you got it. But that puts the minus sign out here. That's where that came from, the chain rule, reverse chain rule type thing. Okay, now evaluate this from 2 to 0. When x equals 2, this is 0. So the whole thing is 0 here. When x equals 0, well, the minus times this minus makes a plus. It'd be square root of 3 over 4 times 2 cubed, which is 8 over 3. Well, 4 will go into 8 twice, so it's 2 root 3 over 3. 2 root 3 over 3. That would be your answer. Now, I thought they skipped way too many steps there, and you probably think I did too, but there is your the volume done that way. Okay, now you might say, why didn't I do it on the whiteboard? I didn't want to try to draw that on the whiteboard and then you to try to figure out what I was talking about. Let me at least do that equilateral triangle thing for you. Okay, so let's go to the whiteboard. I'll at least do that part because I thought that's where they left off the most. Okay, all right, now I'm going to start with a straight line. I'm going to try to make a straight line. I mean, this makes a straight line. I'm going to try to make it horizontal as much as possible. Okay? Now, I'm going to try to do another one of the same length. Okay? And another one of the same length. Now, these obviously aren't quite the same. They're not quite parallel, but I don't need them to be parallel. But what I'm going to do, I'm going to take this one and move it down here. Take this one and move, oh, I messed up. I didn't know, I'm going to try to keep the same length. That's why I drew it that way in the first place. Obviously, I botched it. Okay, why can I not get this one to... I can't. I guess I need to do a select. Nope. I want this one. Okay, there we go. Okay. Now let's just imagine, use your imagination, and assume that's an equilateral triangle. Okay? Now, like I said, I'm going to make up some numbers here. Let's just say that this length here, somewhere right in there, is 1, and this would be 1. That makes this 2, and that's 2. Okay? For any equilateral triangle, those are going to be your thing. This length here is what we're looking for as the height of that rectangle. Ooh, that should be a vertical line. Okay, let's just say that is a vertical line. Okay, and let me go back and erase this one. Okay, now, what I was trying to get at, what is the length of that line? Well, we know from Pythagorean theorem that 2 squared minus 1 squared is 4 minus 3 is 3, so this is the square root of 3. Okay, now that's the ratio for every equilateral triangle, height to base. Okay, well, let's say it another way. If this now were not 1 but x, and this were x, okay, now the area of this triangle would be 1/2 the base, which is 2x, times the height, which is the square root of 3, times x. The x is outside the radical here. Okay? Well, the 2's go out. And let's see. And that would just be the square root of 3 times the base squared. Okay? And I think, so that's pretty much what they had here. Okay, if I can proceed with this again. So the square root of 3 times the base squared. No, it's 1/2 the square root of 3 over 2 times the base squared. I'm sorry, I left off my over 2's. So yeah, that's where you got that. So that probably didn't do a good job of explaining. Okay, but anyway, that was example 6. Okay, and I think we finished that. Okay, all right. They're skipping example 7, and how are we doing on time? We've got 4 minutes. Do you think we can do example 7 in 4 minutes? Frankly, I kind of say no. Okay, so I think we're going to have to begin next time. Now, once upon a time I had a pencil somewhere here. There it is. Okay. We'll begin next time with example 7 on page 460 and 7.2 homework exercises. Do either 5 or 7, they're both at Calc Chat, 5's at Calc View. Do either 9 or 11, they're both at Calc Chat, 9's at Calc View. Do either 11 or 15, they're both at Calc Chat, 13 or 15, they're both at Calc Chat, 13's at Calc View. Do either 17 or 19, they're both at Calc Chat, 17's at Calc View. Do either 21 or 23, they're both at Calc Chat, with 23 being at Calc View. Then do any of the odds 25 to 31, they're all at Calc Chat. 33 or 35, they're both at Calc Chat. Either 37 or 39, they're both at Calc Chat, with 37 being at Calc View. Any of the odds 41 to 47, they're all at Calc Chat. 49 or 51, they're both at Calc Chat. You can explore doing 53 if you would like. It should be at Calc Chat. 55 should be at Calc Chat. You can do 57, it should be at Calc Chat. And then there's some practical kind of problems, 59 through 67. You can do any of those, they should all be at Calc Chat. There's an interesting little blurb on 3D printing on page 463. That should be at Calc Chat. I'm sorry, that was even. Okay, back up. 59 through 67, they should all be at Calc Chat. 3D printing was at 68, so we don't do that. You can do 69. At least one part of that says you need a graphing utility. You may or may not have to have that, but anyway, that's should be at Calc Chat. And I would say stop somewhere about there, and we'll do the rest of those once we finished example 7. All right, any questions? Okay. Hate to do this to you, but I'm going to cheat you out of a minute of your tuition dollars. So unless you have questions, you're going to lose a minute's worth of instruction today. Any questions at all? All right. And by the way, Kira, I just saw your picture and it reminded me, you asked if we could get Physics 213 on the schedule for fall. I've requested it. I can't put it on there. They've taken away my rights, but I've asked the dean to put it on there. I don't know if she's going to do it or not. I'm going to be in a meeting with her after my last class today. I'll try to find out if she got it on there. But you had asked about it. I think some other people asked about it too. So if anyone else is interested, if you've already had your Physics 1 and 2, then 218 is, I think it's called Modern Physics or something like that. All right, any questions, issues, concerns, problems? All right, we'll pick up with example 7 next time. And if you can remind me, tell me not to open 17.2 because there's no more slides on it. So we'll go on and start in 17.3 on the slides, but we'll do the last problem in 17.2. All right, if no questions, I'm going to stop the sharing. I don't like sharing anymore. And I'm going to end the Zoom session. So take care, folks. We'll see you next time on Wednesday. Okay. got Nakia in and 3 more in the waiting room. Let me get them. It's Thomas. David. And, oops, here's Valerie coming in. Howdy. Which one was that? David? No, it was Roy. Okay. Okay, let me get Roy here. All right, I've got 1, 2, 3, 4, 5. Yeah, so far. All right. And how are things going? Well, I do. Well, wait here. Let me get Caitlin in. Okay. And that should be 6 in. That's right. Let me get my PowerPoints opened. I was trying to do it between classes, but I just didn't have enough time. And we are in chapter 19 now. Okay. Okay. And I think we were along about this slide where it was measuring earthquake strength. So I think we were past this slide. Ah, that was the one that we were at. Okay. Now, this. Oops. I can't see y'all. It's in the way too. Okay, we're back. Nobody else coming in. I would have thought someone else would have shown up in that time. That's not what I want. Okay, here we go. Okay. Y'all can see the PowerPoint now, can't you? Oh, okay. Wait, time out.